So far we studied ideal crystal. Ideal crystal is 100% pure crystal, and this 100% pure crystal is obtained by combining space lattice with atomic basis. You know what is the space lattice? Space lattice is nothing but infinite array of points in three dimensions such that each and every point has identical surroundings. And the atomic basis is every point in the space lattice is associated with one atom or more atoms. That is called atomic basis. So by combining this space lattice with atomic basis, we get ideal crystal. And this ideal crystal, identical atoms are at identical sites. Are at identical sites. And this concept of pure crystal is very important for studying properties of the crystal. But in practice, the crystals are rarely perfect. These crystals are rarely perfect. They are not perfect. There is always some defect exists in the crystal. So there are always some defects present in the crystal. But the concept of this ideal crystal is important for studying the properties of the crystalline material. Now these defects are very small fraction of volume. These defects are called crystal imperfection. The defects which are existing in crystal are called crystal imperfections. And this crystal imperfection, the amount of this crystal imperfection is just very small fraction of the volume. Very small. Generally, typically, you can say 10 to the power minus 4, but this is very high. In practice, at room temperature, these imperfections can be in the order of 10 to power minus 70 at room temperature. It means the imperfection is 1 part in 10 to power 17 parts. So the amount of this crystal imperfection is very small. Is very small. Then why do we care about this imperfection? Now the question arises, if this imperfection, if these defects is just a small fraction of the volume, then why do we care? Why do imperfection bother us? Because the reason being simply they affect properties. properties of crystal. And there are two, the major different type of properties. The one type of properties are structure sensitive properties. And other type is structure insensitive properties. These are the two different types of properties. For example, structure sensitive properties. In case of structure sensitive properties, imperfection alter these properties by few order of magnitude. Okay, in case of structure sensitive properties, imperfection alter properties by few order of magnitude. For example, if you take the example of structure sensitive properties like electrical resistivity. Electrical resistivity is structure sensitive property, and its example is semiconductor. So by just adding some impurity atoms from group 3 or group 5, the resistivity of semiconductor changes from 10 to power minus 5 or 10 to power minus 4 to 10 to power minus 2 to 10 to power minus 1 ohm meter. So you can see here by 3 to 4 orders, the electrical resistivity can be changed by the doping. Another structure sensitive property is strength of the material. Take the example of steel here. The steel generally is having 250 megapascal strength. Strength of this steel is 250 megapascal, which can be changed to 2000 megapascal by introducing some defects in the steel. So these are the structure sensitive properties which are changing by few order of magnitude. And another type of property is structure insensitive. Structure insensitive properties are like elastic modulus and or density. Density is also structure insensitive properties. By just having few imperfection in the material doesn't change the density much. We can say that it remained almost constant. So it is a structure insensitive properties. And that's why, we have to study the crystal defects or crystal imperfection because many properties are affected by these imperfections. The properties such as mechanical strength, ductility, crystal growth, magnetic hysteresis, dielectric strength, and as I said, semiconductor properties changes because of changes by a few order of magnitude because of presence of imperfections. So these imperfections are four different types based on the geometry. So on the basis of geometry, there are four different types of imperfections or defects. The first one is point imperfection, or you can also call it point defects. Second type is line defects. Third type is planar defects. And the fourth one is volume defects. You can either call it defects or imperfections. Now, what is a point defect? In point defects, there is a missing atoms or atoms at irregular position. In case of point defects, few atoms are missing atoms. Point imperfection can be, single or double or tri point defects. So there are missing atoms, or you can say there can be atoms at irregular position. That is, atom is not at its regular position, but something at different positions. And there are few different types of point defects, like vacancy, interstitial defect, there is substitutional defect, and Tranquil and short key defects. So these are different types of point defect. Then there is a line defect. In the line defect is comparatively large with respect to point defect. In this case, group of atoms are missing. You can say group of atoms missing, or you can say group of atoms at irregular position. And there are two different types of line defect. These line defects are also called dislocations, and there are two different types of dislocations. One is edge and other is screw dislocations. So that is the linear defects. Then third type of defect is planar defect. Now planar defects are also called surface defects. It is also called surface defects. And these defects are nothing but interface between homogeneous regions. It is a interface between homogeneous region. These homogeneous regions are perfect themselves, but there is a boundary, a surface boundary between these two homogeneous regions. An example of this, which we already studied, like a grain boundaries. The two crystals or different crystals are separated by boundaries, which are called grain boundaries. Then, second type of defect is stacking fault. Second type of planar defect is stacking faults and external surface. These are the different types of planar defects. Then the last one is volume defects. Volume defects is nothing but the big void in the material. In this case, large atoms are missing. Like, during the crystallization, if the air bubble is trapped, and so the size of air bubble, there is no atoms in there. So that creates, the porous. Materials become porous because of this volume defects. So these are the different types of defect, as I said, point, line, planar, and volume defects. And let's go one by one. So first, we will study point defects. Now, the properties which are affected due to point defects are properties affected due to point defects are conductivity and conduction type. The best example is semiconductor, extrinsic semiconductor, p-type and n-type semiconductor. Second property which is affected by point defect is color. And best example of this one is ruby. Now ruby, it is actually aluminum oxide. Aluminum oxide is a transparent material, but in that 0.05% chromium atoms are added and that becomes ruby and whose color is pink. This pink color is because of these chromium atoms. Similarly, transparency is affected, diffusion and mechanical properties are affected because of the point defect. Now let's go one by one. The first point defect is vacancy. The first point defect is vacancy. Let me show the diagram for this. I will insert the diagram there. As you can see in this diagram, there is a vacancy at this position. Here, there is a vacancy, that is one atom is missing. So, vacancy defect is nothing but the lattice position is vacant. In this case, a lattice position is vacant, or you can say atom is missing from that position. So what happens, why this vacancy is created? So at high temperature, what happened? At high temperature, these atoms gain the energy and they start vibrating about their mean position. And if the temperature is further escaped, atom changes the position. Atom changes position, and thereby the vacancy is created. It is because of the temperature. Atoms start vibrating about their mean positions, and at certain temperature that atom escapes from that lattice site and the vacancy is created. Now this vacancy can be single vacancy, or there can be divacancy, or even there can be trivacancy. Now to find out number of vacancies produced at temperature, because these vacancies increases exponentially with the absolute temperature. Now vacancies increases exponentially with absolute temperature. Temperature T. And to find out the number of vacancies, there is a formula which is NV. NV is nothing but number of vacancies, and that number of vacancies is equals to Ns, that is number of regular sites or atoms present, exponential of minus EV by KT. In this case, let me write here, NV stands for number of vacancies. Ns is number of regular lattice site. Or atoms. K is obviously, you know, that it is Boltzmann constant, and T is absolute temperature. So we can find out number of vacancies using this formula. So that was about the point defect. Then we will go to our next point defect, which is interstitial point defect. Next defect is interstitial point defect. Let me show you the diagram for that. You know the what is the interstitial? Interstitial position is that position between the lattice sides, somewhere in the lattice sides. It's not a regular side. It is in between somewhere of lattice side. And in that lattice side, some atoms occupy that position. Okay, this is interstitial point defect. As you can see over here, that this atom is occupying interstitial position, and that defect is called interstitial defects. So how these vacancies are created? These vacancies are created when atoms fall into interstitial position. Atom falls into interstitial position. And that atom, we can call it interstitial atom. And because of that, as you see here, this interstitial atom push surrounding atoms away. And that's why the distortion is lattice is produced. Okay, this interstitial atom push regular atoms away, and so the lattice plane is distorted. Distorted. As you can see, these are the lattice planes, and these lattice planes are compressed near the interstitial defect. Now, there can be different types of interstitial defect. One is self-interstitial, interstitial. Self-interstitial means parent atom occupies interstitial position. That is called self-interstitial. And if there is a self-interstitial, then distortion is substantial. And another type of interstitial is interstitial impurity. The first type of interstitial defect is self-interstitial, and second type of interstitial defect is interstitial impurity. Interstitial impurity. As the name implies, in this case, this interstitial atom is of foreign species. Interstitial atom is of foreign species, such as carbon, It can be nitrogen, it can be hydrogen or oxygen. And if there is an interstitial impurity defect, then obviously the size of these atoms is small compared to size of parent atoms. And so in this case there is less distortion of lattice planes. Now this interstitial impurity also can be single or di or tri interstitial. So that was about the interstitial defect, point defect. So in this case, there are two types of point defects. One is self-interstitial, where interstitial atom is of the parent at, uh, material, and in that case, distortion is substantial. Another type is interstitial impurity, means interstitial atom is of foreign species, and in that case, there is a less distortion because this interstitial atom of foreign species is smaller compared to parent crystal atoms. Then let's go to the next point defect, and the next point defect is substitutional. Substitutional point defect. Substitutional point defect, let me show you the diagram. This is the diagram of substitutional defect. Now, as you can see, substitutional means atom is replaced by different atoms. Okay, substitutional impurity is nothing but parent atom is replaced by atom of foreign material. Foreign, let us say foreign species. Now that atom can be smaller or it can be bigger. Smaller or bigger compared to parent material atom. Now, if it is a smaller, as you can see in this diagram A, this atom is replaced by the atom of foreign species, but that atom is smaller. And when it is a smaller, the tension is produced there. Tension in lattice plane is produced. But when this atom is bigger, as shown in the diagram B, this is the atom which is a bigger compared to the atom of the parent material or parent crystal, and so it produced the compression in lattice plane. So that is the substitutional defect, substitutional point defect. Then we will go to the next defect, which is a Frankel and Schottky defect. Frankel and Schottky defects. Point defects, obviously. These Frankel and Schottky defects are observed in ionic crystals. They are present in ionic crystal. And you know that these are the ionic crystals, so the defects are charge defects. Defects are charged. In ionic crystals, there are positive ions and negative ions. So, the defects in ionic crystals are charged. However, charge neutrality is maintained. How the charge neutrality is maintained? Let's see that. First, let me show you the diagram. You need to draw the diagram in the exam. So this is the diagram of Frankel and Schottky defects. And this is the example of NaCl. As you can see, there are arrays of sodium ions and chlorine ions. So here, the example I have shown here is of NaCl. It is a two-dimensional diagram. So let's first see what is the Frankel defect. Tranquil defect is shown here in this diagram by the symbol 1. As you can see here, this is the Frankel defect. And you can see there that there is cation vacancy. The bigger are anion. This is anion, which is chlorine in this case, and smaller are sodium ions, so which is cation. And in the diagram here marked by 1, as you can see here, there is a cation vacancy and the cation is at interstitial position. So Frankel defect is a pair of, you can say pair of cation vacancy and cation at interstitial position. So there is a one vacancy here of the cation. The cation is missing from this point and it is shifted to the interstitial position. So the number of cations overall are the same. They are not changed. So the charge neutrality is mentioned. And so this defect is called Frankel defect, in which charge neutrality is mentioned, and it is nothing but cation vacancy and cation at interstitial position. There also can be anion vacancy, one anion vacancy, and one anion and anion at interstitial position. But since anions are bigger in size compared to the cations, so these are the rare. Anion vacancy and anion at interstitial position is the rare. Generally, what you see is cation vacancy and cation at interstitial position. Charge neutrality is maintained, and that defect is called Tranquil defect. The next defect is Schottky defect. Schottky defects is marked by circle 2. Circle 2 in this diagram. You can see in this diagram, this is the circle 2 or oval 2, and you can see that there is a cation vacancy. One cation is missing here, and one anion is missing from this position. So when only vacancies of cation and anions are present with no interstitial or misplaced ions, that defects are called Schottky defects. So Schottky defect is nothing but anion vacancy anion and cation vacancies, and no misplaced ions or no ions in interstitial position. No misplaced ions, or you can say no ions at interstitial position. There is just a vacancy of anion and cation. A pair of anion and cation is missing. Then that defect is called Schottky defects. And these defects are always nearby. These both the defects are nearby defects. They, we can say, this defect stays near, and so charge neutrality is maintained.